the reason why have it separate is because we'll generally be dealing with commutative rings in the case of lattice-based cryptography. That's what we're going to deal with. And a ring. So there are only 3 more slides. Bear with me again. You can always go back to the slides in the future. So using a paper, group, ring. Yeah. And this is one of the goals of.
So these 3 slides are going to be in our group sheet as we're reading the papers, right?
Yes. Yes. I mean, again, order and portions, we need to understand those.
Yeah.
So what is ring? So to simply, so in the case of ring, we have 2 operations: addition, multiplication. With respect to addition, ring abelian group, we mean that all 5 properties that we discussed are satisfied for the operation of addition. And again, the set of integers is a very good example. So all 5 of those properties. However, for the second operation that we have defined here, multiplication, only 2 of the properties are satisfied here. So, and the term monoid for this type of, which is a generalization of group, but generally speaking, for the operation of multiplication, we have the rule of associativity satisfied, the property of associativity, and we have and we do have multiplicative identity. What we do not have is we do not have support for commutativity. So going either swapping the terms in the case of multiplication, extremely important, we do not have the property of multiplicative inverse. That multiplicative inverse is going to be very important for all our future discussions. And one more property that combines both of those operations and multiplication is the property of distributivity. Again, you've probably seen it in high school algebra. That one is easy to interpret. And so those are that's what's called the ring. So when we hear the term polynomial ring, all properties are automatically satisfied, saying that it's a ring. And our definitions, and there will be one more slide with ideals after this, and then we'll.
There's always one more, right?
Of course.
When you're doing crypto, there's always a little bit more math.
Of course. Commutative ring. It's a ring, so all the properties we've discussed so far are satisfied. In addition to that, the property of commutativity is also met.
Yes, so actually we had a question from Daniel Carr. Daniel, I'm just going to read your question unless you want to say yourself. I can come off mute or something. Is the third multiplicative distribution required to be stated or is implied by a monoid abelian group?
Is the third the closure is what was I'm trying to what's the third what's referred to? Let me go back to the previous slide.
Daniel, slide you mean? Yeah, this slide is the third multiplicative distribution where to be.
Distribution. It's actually that's a different property because it combines 2 operations, addition and multiplication. So it's not something that applies to one operation only, like in the case of group. So it's basically a combined property. That's why it's called this. I mean, because if you see both multiplication and addition are involved, that's why they're interesting. In the case of group, we only focus on one operation. So that's and this is ring is a combination of 2 groups in a sense. That's really the general logic. One of the group is everything abelian group. The other group has restrictions.
Great. So Daniel just said understood.
Okay. So yeah, just do this slide and the next one. Sorry guys, but we have to go through this stuff. So commutative ring. Everything that we saw for rings is satisfied. In addition to that, the property of commutativity is also met. And really, polynomial rings is a great example of commutative rings. So what we'll be dealing with will be commutative rings, polynomial rings. So everything we'll discuss, probably starting more with the next lecture because we won't get into the polynomial part this time.
Sure.
But it's very important that when you see commutative ring, that's what it means, and that's really the polynomial for us, generally speaking. Then I do want to mention one more concept, a field, which I'm sure you've seen many times, and probably many of you know what it means, but that's for the sake of generality and also to understand how the algorithms we're going to discuss compare with the traditional discrete logarithm problem. So a field is a commutative ring supporting the operation of multiplicative inverse for, of course, non-zero elements. So it's a field is a ring that supports the property of commutativity and multiplicative inverse. So in a sense, complete set. So both addition and multiplication in this case represent abelian groups. So that's the definition. What fields are important? Because fields we usually deal with in the case of discrete logarithm problem, in the case of regular number theory, if we have let's say P, a set of integer numbers limited by a certain prime number, P, then that particular set will always called a field. If, however, because this is why it's called the field, because any number up to the prime P will have a multiplicative inverse in this case, as we know. If, however, we have instead of a prime number, we have as the subscript a composite number, for example, in this case 14, this particular set will no longer be a field. It will only be considered a ring. And everything that, when we talk about discrete logarithm problem, regular number theory, we talk about the cases when we have the base 2 to the power of n, or p taken to the power of n, or simply prime number. They are examples of a finite field, or it's also called Galois field. When we talk about elliptic cryptography, the same thing. Talk about operations over fields, generally speaking, and discrete logarithm problem applies in this case. So field is more restrictive. And when we discuss lattice crypto operations later on, and especially when we deal with prime numbers or certain operations based on prime numbers, such as roots of unity, etc., this concept of field will be important. So this is the reason why we need to understand that.
Why zero 13 is a finite field and zero 13 is a commutative field?
In the case of Z14, multiplicative inverse is not defined for all elements from 0 to 13. That's why. If you remember just the extended Euclidean algorithm, find the modular inverse, the condition that two numbers have to be co-prime. And this is what, if they are not co-prime, and in the case of 14, we'll have those situations, then we will not have multiplicative inverse for those situations.
So multiplicative inverse, so those of you that might not know, is where you can, think as a multiplicative inverse mod, say 13, I mean, resist a number from 1 to 12, that you multiply by that number, you get 1, mod 13. And this for the field from integers of 0 to 13 exists for 14. I think I agree with the 14, right?
Yes. In the primarily, and although it's not mentioned here, you will often see in Lattice crypto papers you have Z and certain subscript corresponding to the actual prime base. You will often see the star symbol at top. Usually that star symbol only includes those elements that have multiplicative inverse. Very important, because I've seen it in a lot of Lattice crypto papers. And the reason we have the star, because the base in case is not a prime number, and there are chances that, and our focus will be only on those elements that do support multiplicative inverse. And actually, when we we talk about the difference between Chinese remainder transform and discrete Fourier transform. The one difference comes basically because of that star, whether where it's defined, where it's not defined. But
so this is actually something I want to bring to everyone's attention. There's this key operational, crypto primitive we use in Lattice crypto called remainder transform. So like something called discrete Fourier transform, something we're probably very familiar with if you have like an engineering background. It's popping up a real lot. It's almost the prime computational bottleneck. These kinds of things, whether you're doing cryptanalysis or crypto or homomorphic encryption, and so if you're going to be doing work in this group, you're going to be spending a lot of time becoming very familiar with the CRT and its pains and pleasures and all that kind of good stuff like that. And how to use it and when to deploy it and whatnot. And I think it's pretty important for this is exactly what you were getting at, this set called Z star sub P. Effectively, I believe Z star sub P is effectively everything that's coded with P.
Yeah, it's the same way. If the fact that there is a multiplicative inverse means that it's called for the actual number.
Yeah, so that's another way. I don't think that's necessarily a definition, but it's effectively how it works out.
Yeah, it's very important, and that's one of the reasons why I also wanted to discuss the definition of field, because in the case of a field, that Z star is equivalent to all elements in the field if it's a prime. If it's prime, then we are with a commutative ring, and only the star part is the one that has multiplicative inverse. We're going to see it a lot in Lattice crypto problems.
Yeah.
Okay, the last one on algebra.
Sure. You have a question?
This is Megan from SSCPAC. I was wondering, in study of this, is there any kind of intuition that you can give us on the naming of the fields? Because it kind of helps relate the structure. So groups can make sense, and rings that they loop back into themselves make sense. But what about the fields? Intuition on the naming.
So let's think about it. So it's whenever multiplicative inverse is defined. So one way to differentiate between fields is like we discussed. If it's a prime number, then it's and we are dealing with a certain set of integers up to that prime number. I mean, limited by prime number. Then that's going to be a field. If it's not prime, then that's not going to be true. I
think maybe the question, Megan, to maybe interpret this is that it's some sort of mnemonic device that helps distinguish what fields actually represent when we use that terminology as opposed to rings or groups or anything else.
I'm just trying to get to the core concept of what it is. Like the ring, how the operations will loop back into themselves, or group is like a loose conglomerate with the properties. I'm just wondering if, like, why they're named fields and
there are a couple of things that can be done. I mean, one is if you picture groups, rings, commutative rings, and then fields, and you can use this circle. So group would be the large circle. Then you could inscribe in that circle the circle of rings. Then inside that circle, you will have commutative ring, and then further inside you have the field. So that's one way to present it. So in other words, the field is the most, the one that supports the most number of constraints, most number of properties. So that's one way just to work the hierarchy between them. So the group is the most, and we started with the most general one and went to the least general one, which is called the field. And in my mind, the of relative coprimality. That's a very important concept. So that's again, maybe from the intuition perspective, I'm not sure if it's easy to grasp. Maybe when we go through certain examples, we'll see that. We'll start with that, inscribing circles. Well, let's start with that definition. And as we look at more examples later on, I think we'll have certain associations in our head, and that a little bit kind of separate from from those abstract definitions, but we have to start somewhere. Yeah, I would say that's.
Maybe we should try to get something a little more graphical to put together. Just kind of.
Yes, we'll add some material probably. We'll do that. Maybe we'll add an extra slide showing that.
But yeah, so the question, this essentially helps identify some of the holes in our explanation also. Some things maybe we need to do a little bit better for the students as we're doing this. So.
Okay, yeah. So the next concept is the last mathematical concept, I mean truly mathematical concept. Of course, we'll discuss the mathematics after this, but not at the level of definition. Ideal, and why ideals are important, because we will be dealing with a special type of lattices, and lattices will be introduced later today, and the special type that we will be dealing with is ideal lattices. That's why it's extremely important. Yes?
So we actually got a really good comment from David Wasserman. David, I'm just going to read it off. Says maybe you could think about complex numbers as an archetypal field. Complex numbers look like a cornfield or a soccer field, and finite fields look very different.
That's what I was looking for. Thanks, David.
Okay.
Yeah, I see. Maybe also part of the question, finite and infinite. I think that was part of the question that probably missed. Yeah, because finite obviously means when we restrict, when we work only with elements from 0 to p minus 1 in the case of years. Okay, yeah, we'll try to put some graphical representation of this, just a little bit easier to quick read a paper. You look at that picture. Yeah. Okay, I know where I am. So we'll try to
put it as a big poster up in the lab.
Yeah, yeah, it's a very good comment, and I know it's some stuff is not intuitive. It's not meant to be intuitive.
Yeah.
The history behind group theory, but I'll skip that right now. Ideal. What's ideal? And probably, although the definition is given here, I'll start with examples. Let's say we have a set of integer numbers, z, and is going to be a subset, or in this term, subgroup. Example of an ideal is all even numbers of which is just denoted as 2z. So in other words, 0, 2, 4, etc. And now let's go back to the more formal definition. So you have a certain group. Take a subgroup, a subset of that group. So only selected numbers. In this case, 2, 4, 6, etc. Instead of 1, 2, 3, 4, 5. Then, so we selected the subgroup. We observe that for that subgroup, multiply any that subgroup by any integer. In this case, if we multiply any even number by an integer, we will always get a result in a set of even numbers. So in other words, so in the case of ideals, even numbers will be closed under multiplication. So, and in the case of even numbers, if let's say we have an even number, let's say we have number 4, and multiplied by any integer, 1, 3, 4, example, the result will always be even. And the same logic will apply to lattices and ideal lattices. And the lattices is a general concept, and ideal lattices is only a subset that satisfies certain properties. So we'll discuss, of course, the definition of ideal lattices later on. It's a subset with special properties, allow us to always stay in that subset. In other words, in the subset of even numbers. Mathematically, the definition of mathematically, but I try to use basic concepts. So even numbers multiplied by 3, by a number, immediately give you an ideal. So that's
once we start getting into the crypto protocols, I think a little bit more.
It'll be more. Yeah, unfortunately, but it's definitely ideal is always a subset. of something that's, and this subset has special properties. And
hierarchy of the field or the group.
Ideal is so it's let's say if you have a ring, an ideal of that ring is a subset of that ring that has a certain closure property for subset, just simply speaking. So the concept ideal can be applied to rings. It can apply to fields. It can be applied to any of the what we discussed. So it's somewhat separate. It's a special subset of the entity we're dealing with that has that property of closure. That's generally speaking. So in the case of ideal lattices, it's going to be a subset of overall lattices that support this property. And when we see examples, and we'll see some examples later on, we'll understand it a little bit more. Okay, so I would say that's the glossary we need to know. And maybe we'll have certain graphical representation. Now let's start talking about lattices. And again, lattices is going to be something somewhat you can still visualize it.
So maybe we should pause for a second. I know we've been talking on this side. We're going to move on to the next section. Are there any questions or comments? Okay.
That would be the concept, the comment.
Yeah.
Okay, we still need those definitions.
Yeah, no, you're right. I just wanted to make sure we pause for the people that are online.
Okay.
Yeah.
Lattices. So this is somewhat, but at least we'll have a visual representation. So in the past, you probably dealt with a set of real numbers, and R generally represents a set of numbers. And for example, we can talk about the regular Cartesian coordinate system with tangential system, which is generally denoted as R2. In this case, we will be dealing with a certain n-dimensional system of real numbers. So Rn means it's a relation from
individual Cartesian space.
Simply speaking, simply speaking, if you go from dimensional regular plane coordinate system, you go to three-dimensional, you add one extra axis, and it becomes R3. So in this case, it's Rn, certain generalization of the n. We often see that in mathematics. It means that to represent every point on that vector space of real numbers, we need the number of coordinates that we have n that correspond to the dimension. I mean, again, I'm slightly simplifying it. Mathematically, it's not always correct, but generally speaking, that's what this means. Then in this, so first of all, we start with that n-dimensional space, and in this case, we're dealing with Euclidean space. And Euclidean space, and maybe you've heard this concept, but the general idea is how you measure the length between points on that in that n-dimensional vector space. And Euclidean space implies that you take the square and then you take the square root. So the no definition of length between two vectors that I'm sure you studied in high school or in undergrad studies. For any vector space with the product, so multiplication in a sense, that's obviously given, and then we also define the norm, and the norm is how we actually measure the length in that particular vector space. So what that is? So is a discrete subgroup of this n-dimensional space of real numbers. And when we say discrete, again, in your mind, you can think of we're only looking at, for example, integer numbers. Generally speaking, we will be looking at integer numbers. Instead of having any arbitrary number in that n-dimensional space, we will only work with integer numbers. So so that's a simple example of the discrete subgroup. So it's definitely a subset of what, and all the possible points on that lattice, and lattice is again discrete subgroup, are have a discrete set of points, and there are certain, for example, we can measure distance between those points, and we can only have values at those points in comparison to the dimensional space. So this is what's important about discreteness. So lattice is something that they have a cyclic structure with points repeating over in various dimensions with certain interval. Question. The norm W, I didn't see the end of it, but I understood the question, is defined in terms of Euclidean distance. I think that was the question.
Yeah, so a normal, sum of square root of
yes,
squares.
It's a normal square root of squares.
Is the square root of squares, or is the nth root of power n?
No, that's now you're talking about more generalized definition.
Yeah.
So the Euclidean definition is, so it's called L2 norm. Yeah, L2 norm. So I mean, again, so L2 norm means that we have the operation squaring under the square root, and then we have to take the square root. So that's we're only, so those of you again who are familiar with L2 norm, this is L2 norm. So Euclidean space corresponds to L2 norm. So far all we have is just vector space with certain points that are allowed. Not all points, like in the case of real numbers, are allowed. In this case, only again, something corresponding to integer numbers. And what are the different ways to look at the lattice and how to define a lattice? Just like any vector space, there are two common characteristics of lattice. One we already discussed is the norm, how the distance is defined, and second is the basis, and means linearly independent vectors that can be used to represent a point or vector, if you use that concept, on that lattice. So we have basis and norm, two important concepts that are defined for lattice. And mathematically, this definition that a lattice can be represented as a matrix. And in that matrix, we would have the values of the components corresponding to every vector in the basis. So that matrix itself that we apply to any that we use to define any vector on that represents the coordinates of all the vectors in the basis of B1, B2, B3, B4, etc. So generally speaking, lattice can be represented as a matrix. And we find certain vector on that lattice, that position corresponds to a matrix product. So you have a matrix corresponding to the basis, to the vectors in the basis, and you're multiplying it by certain vectors. So that's the general, mathematically speaking. And when we talk a little bit later with ideal lattices, it's called to use for efficiency's sake that matrix to a vector. So that, and we'll discuss it in more detail during the next lecture. But the idea is you have a matrix, and it's from the efficiency perspective, it's a very
sorry, I didn't mean to interrupt. So the question is that come from SSCPAC was what's Z represent? So Z represents a set of integers.
It's a set of integers. So in other words, the conditions in front of those basis vectors are just integers.
Yeah. Unfortunately, we saw these slides and we have kind of a funny font on them, so they're kind of a non-traditional representation of the Z, but yeah, that represents the integers.
And again, just to take away from this, what's important is the basis and the norm. So in our perspective, the norm is defined using regular Euclidean space, so it's just the way we measure length between, for example, length of a vector or between two specific points. Basis is extremely important. The hardness, the mathematically hard problem that we'll discuss later are actually related to the reduction of certain bases that we have to an orthogonal basis with certain properties. So that basis is very important from the mathematical hardness perspective.
So yeah, so that's actually a really good point. So notions of bases come up in a lot of strange places. You know, me being a control theorist from my educational background is control theory. You know, the way about it is the basis is basically what defines these large multidimensional set of points you can reach from integer summations of these various vectors, both positive and negative summations of these vectors. And the notion of linear independence is very important in the context of computational hardness. You know, vectors you might think about, like the two vectors we have diagram right here. You know, there's almost a right angle between them, not quite. The more these vectors that you have that are orthogonal to one another, the more right angles you have, or closer to perpendicular you have, the more secure your crypto system is that you build upon these basis vectors. And I know there's a couple students here and probably some guys out in San Diego that are interested in the security of these crypto systems and maybe even how to crack these crypto systems, is that the more these vectors get closer to being parallel to one another in the higher dimensional space, generally computationally easier becomes to actually crack these crypto systems. And so to define these bases, to define a crypto system, how orthogonal, how perpendicular they are in the higher dimensional space becomes really, really important. And understanding these, how, you know, the closeness of linear independence and how orthogonal they are is something that's going to be a really heavily repeated issue. We're going to be beating that drum a real lot as we get to like specification and prioritization of these crypto systems.
Yes, actually, there is maybe you've seen it. There is a so-called LL reduction procedure. That's
the LL algorithm, and we'll see that a real lot, particularly as we start doing cryptanalysis.
And,
stuff like
yeah,
that.
and it's related to transforming from a certain basis to a more orthogonal basis. And again, this is something that's used a lot in proving the hardness that certain lattice problems are NP hard.
Yeah.
So this is, and basis is something that defines this lattice. So that's also very important.
Yeah, and particularly if any of you like me are coming from more of like a control or signal processing type background, a lot of you might have built up over the years to start to actually think about these systems like the D, like lattice bases are actually quite applicable, actually dealing with things in this integer space as opposed to the complex domain. I believe LLL. What I think one of them is Lopez-Alt. What
Last names. They're actually the last names of the scientists. It's Lesla. I mean, I cannot remember the last name.
I think there are a bunch of Hungarians.
Yes,
yeah.
There's the last names of the people, of the scientists who invented it. Let's actually discuss that a little bit later if that's important. I don't think we're going to need to get into dive into that particular routine itself because it's used more as a tool for reducing from one to another and to prove the hardness. Something that's very important for
I've seen it applied for cryptanalysis of lattice crypto systems.
Yeah.
And so I think that we'll want to have a lecture or a seminar or conversation in a couple weeks, a couple months that actually focuses on cryptanalysis because that can actually be very helpful for parameter selection.
Yeah.
Anyway, so get into the concrete use of these things. And
yeah.
So I actually want to really focus on that quite a bit later on.
Yes. Cryptanalysis, you cannot do any cryptanalysis with those basis reduction operations.
Yeah.
Yeah. I have one question that you said that if two vectors are perpendicular to each other, then the code is more secure.
Well,
how to find if these two are perpendicular in the bottom?
Well, there is Gram-Schmidt or orthogonalization procedure that drives it, but I think I would rather defer that discussion to that a lecture when we discuss LL reduction because then we'll get a little bit more.
Yeah, I think that we'll try to get that a little more concrete when we actually get to cryptanalysis because that's a really interesting question that pops up in a lot of fields, not just crypto, but signal processing and control systems. You know, as you start to do these, you get a more robust control system. And, you know, a lot of practical importance for, you know, why lane fly safely.
Okay. Yeah, any type of tensor analysis, for example, uses all those operations. So the operations that we discussed here are not simply applied to crypto. They're used in computational multiphysics. They're used in many other places. So it's a generalization. The reason why those those concepts of groups, rings were introduced is because they apply to so many different fields. And actually, when I dealt with partial differential equations, symmetry groups, Lie groups were induced there at some point. But
this actually is going to be an important thing as we're doing research in this area, is that it's not all coming from whole cloth. It's just not crypto systems. Like, I had a long conversation last night about applying single processing techniques for the FFT to CRT in computational space, computational domain. And we're going to have to be very mindful of who broad where the deep well we're pulling from for this. We have a line when I was working at VPN is we'll steal a good idea from anywhere and steal good algorithms from any place we can to actually make this stuff run fast and practical.
Yeah, that's a very important concept. So I won't focus much here, but there is a concept of lattice. There is a concept of lattice volume, and really, if you think about it in terms of a two-dimensional space, we're referring to square. If we're talking about, in the case of three-dimensional space, let's say Cartesian, we're talking about something like a cube. So that concept can be generalized to n dimensions, computed the same way. It's a way to measure the elementary volume of the lattice. And I don't want to spend too much time on this, so we'll just look at the slide. What's very important regarding lattices used in the crypto world is that the matrices that we deal with and corresponding integer lattices are generally full rank. So whatever matrices we have use all the columns and rows that are defined there.
So basically that means is that for any one lattice, you can't express that any one vector in the basis. You can't express any vector as an integer summation of other vectors.
That's correct. They're linearly independent. That's very, if they're not linearly independent, then it reduces to a much smaller problem, and from the crypto perspective, that becomes not secure.
Yeah, and also from a practical perspective, it means that you're basically pushing around way more data than you need to.
Yeah. So there is a full rank. So speaking, if those integer lattices correspond, we're going to deal with corresponding full rank matrices.
Sure. So there's a question we have from SSCPAC. Is there a relationship between the volume and the determinant of the lattice?
Actually, there is. So both of them are independent of the basis. So they actually compute. I mean, those characteristics are computed, and they produce the result no matter what basis you use. So it's actually they belong kind of to the same space. So I mean, determinant and volume are related definitely. Those are characteristics that abstract out from the specific selection of the basis. That's just a simple. So they're objective characteristics that okay. So so the next concept is problems. So a question
doesn't have to do with anything.
Well, it's very interesting. I can actually read that diagram because so it's Russian. So basically it's Russian, and it has Mohammed Al-Khwarizmi, so the one who came up with algorithms.
Oh, okay.
So that's and I obviously he did some initial some really early analysis, but I mean he came up with the word of algorithm, the complexity of algorithms,
okay.
And I think. Nguyen is the scientist who, that we used. We adopted the slide from. I think he probably had Russian background. Let's put it this way.
Sure. Okay.
Or so lattice problems. This is actually extremely important. Lattices are. Why are they needed? Why are they so exciting for the field of cryptography? Because there are certain problems in dealing with lattices that are NP hard, so non-polynomial, non-deterministic polynomial hardness factors apply to them. In other words, it was mathematically proven that certain problems are very hard to solve, and actually very hard to solve even using algorithms of quantum computing, such as Shor's algorithm. So the motivation behind lattice problems is interest to traditional discrete logarithm problems, factoring problems that are believed to be hard. These problems were shown to be NP hard, and more, they were shown to be NP hard for the case of quantum computing. And a traditional discrete logarithm problem and factoring problem, they are not immune to, I mean, obviously there is a known Shor's algorithm that can solve those problems in polynomial time. So that NP hardness, especially with respect to classical computing and quantum computing, which makes lattice problems very appealing.
So yeah, I want to put a finer point on this. This is a very, very important aspect of what we're doing and why we choose lattice crypto besides the functional properties for homomorphic encryption. The code building on lattice problems, which are hard to solve with a quantum computing device, and our crypto systems that we build are what's called post-quantum. We will attacks even by quantum computing devices if you have one and become broken. And another part, I think you're actually getting this worst case analysis versus average case. Yeah. The hardness problems are defined with worst case hardness. You have some sort of one canonical, very kind of set of problems which are very, very hard in the worst case, and really a bit stronger than what we call average case hardness. And so you sometimes have I don't know how it actually translates into a practical sense of security, but it basically gives you a minimum level of insurance that you don't have with the other more traditional crypto systems.
Yes, so and we'll talk about this a little bit. So generally speaking, for certain problems, learning with errors, LW, we discussed, the average case scenario can be reduced to the worst case hardness for lattice problems. And the complexity of average case scenario of implementing a certain algorithm based on a certain problem, like LW, is equivalent to the worst case complexity of a lattice problem that's considered the most secure way possible. Because in the average case, you will always have the worst case hardness. That's just simply speaking, and we'll discuss this a little bit.
I just want to take a quick time check because we're getting on an hour.
Yes.
Yeah, so we got a lot of people online, and I want to be very mindful of everyone's schedules, particularly these good people out in San Diego, national security, right? And so we want to make sure they
That's
can
right.
So I think our little group here is probably fine to continue for a little bit longer. If other people have to move on to meetings or whatever, thank you for joining us, and we'll be doing this every week, so we hope you'll come back. But
So
if you stick around for the rest.
So one thing I am doing is I started recording this, and so I was going to keep this private. For anyone on our little cabal that wants to listen in on this later, go back and revisit it. How much more minutes do you think for the slide deck that you have?
I think it's actually going to be a little bit faster. I think we could do it in by 5 o'clock we should be done Eastern time. It's 25 minutes if the word, again, something done shorter, quicker, something.
Yeah, I want to be, like I said, I want to be mindful. So maybe we can do it in like 10, 15 minutes and something spills over to next time. Sure, do that next time. So, like I said, I'm recording this. I'll make it available to anyone who wants to have access to it. We'll wait for it to go for maybe another 10, 15 minutes to get to a good concluding point, and pick up next, same bat time, same bat channel next week.
Sure.
So, okay.
So, what are some of the problems that are defined for lattices? So the two main problems and all other problems are derived from the shortest vector problem and closest vector problem. And so what is the shortest vector problem? Let's say we have a lattice, and we're given a basis of digital lattice, just like we discussed in the past, and we need to find the non-zero vector in lattice that minimizes the distance of that vector. So the shortest vector in the lattice itself. So and this is just illustrated for this particular lattice and the visual representation. We see this shortest vector is different. And the problem of finding the shortest vector is actually closely related to the algorithm for reducing the basis from a certain form to an orthogonal form. So that's actually the operations of reducing the basis are related to the hardness of this problem. So you can believe the lattice community that it's very hard to solve this problem of finding the shortest vector. You're given basis, a matrix representing that basis, of course, for certain conditions. So that's what that problem means. In this case, it's shown that the worst case complexity of this problem is hard. So this problem is NP hard in the worst case scenario. Okay, and that problem that's given. Those are the two core problems. It's the closest vector problem, and so we're given a certain lattice, and we're given another vector that's not part of the lattice, and we need to find the closest vector between that vector t and a certain point on the lattice which is nearest to the vector. There is actually a slightly refined version of this problem called bounded distance decoding, which is with a case where the distance from that vector t to a certain point is bounded by certain value. So and those two problems are at the core of analysis for lattices. To give an idea, without going into details, these are some of the common problems that you will see in lattice crypto papers, especially the shortest independent vectors problem and the boundedness decoding. A low hardness analysis actually shows that whatever formulation we have in the case of ideal lattices be reduced to these problems.
Yeah, generally these things are variations of a theme, for the closest vector problem as you defined it.
Yes, yeah. And sometimes shortest vector. So it's actually between the those first two are at the core of the analysis. And we'll go to the next topic. So on one side you have lattice problems. You have some other hard problems that are typically for matrices that were not introduced specifically lattices, but that were, for example, like in the case of learning with errors, that particular problem was formulated in machine learning. So in the artificial intelligence field. So there are certain known complex problems dealing with matrices, and math research showed that there is some equivalence between the lattice problems and these two particular problems, the SIS and the learning with errors problems. So shortest integer sum and the learning with errors problems. And we'll take a look at how those problems are connected actually to lattice crypto real quick, and just to keep it from the console perspective. We'll mostly be dealing at this point with learning with errors, so cryptomania, so the actual encryption, decryption algorithms. This integer sum problem is used more for so-called mini-crypt scenarios. So one-way, we perform one-way operations such as hashing. They're used for signatures and identification. So our focus will be on the LWE encryption, decryption scenarios. This is just to give you an idea about the worst case, average case. It was mathematically the integer solution problem and learning with errors problems have equivalence to those shortest independent vector problem and the decoding problem, and you see that their hardness in the average case can be used, in other words, is equivalent to the worst case complexity for those two problems. And what that means is that also makes it secure from the quantum computing perspective. It makes them immune to quantum cryptanalysis. So there are two sets of problems, lattice problems, we know a lot about, and two other types of problems that came from matrix world and machine learning, and there is some equivalence between them, and that's used as the basis of crypto.
So I hate to be pedantic, but this is security, and we need to be pedantic for security. And so it's much that they're immune to quantum problems is that they're strongly believed to be immune to quantum. Right.
There is no known algorithm that can solve. Yes, but yeah, and it's not believed that there will be one developed.
Yeah, I go in front of one of my typical government customers. They always like throwing that at me, and that's why I gotta be very careful on making sure I specify that, so I don't want anyone ask me a cheap shot later on, or if anyone has a PhD defense later.
Yeah, and Shor's algorithm cannot be used to solve this. Just which is the best known algorithm.
Which is a popular known algorithm for solving crypto problems in quantum space.
Could you just in brief say anything about quantum computing? Is it really like doing something to solve some problems?
I was thinking, because I can reply. I mean, it's a long discussion.
I think that might be a lecture in and of itself.
I would be happy to give that lecture, but I think it's my answer will at least take 5 minutes right now.
Maybe we should put that off for a couple cycles, because there are one or two very good papers that talks about the relationship of quantum computing to crypto and looks at the match problems. And so that would actually be a fascinating topic, because I know we have a couple of students that particularly expressed interest in cryptanalysis, and that would be a really good thing to talk about as we broaden our understanding of this field. So, but thank you for asking.
Let's look at the definitions of those problems. What do they represent? The integer solution problem and the learning with errors problems. So generally speaking, we're given a random matrix A, and we multiply it by a vector. So we're writing down a set of linear equations in a sense. The problem of the shortest integer solution problem is to find the coordinates of a certain vector, small vector S, and we say small is bounded by some value that will make this set of linear equations, the system of equations, true.
And so, we had a question from SSC Pack. How easy is it? How is the proof of reducing LWE to BDD?
And it's in other words, it
is the reduction.
Yeah,
I mean that's the first question to ask. Is the reduction?
Well, yes, there is, but again, you should differentiate between exact and poly n approximate version.
Yeah, whether you have a polynomial time,
yes.
Linear time, or
it's actually not as straightforward as you would think, because sometimes those reductions are done made for approximated versions of the problems, because it makes it easier. But generally speaking, the analysis is not very easy for any type of reduction. Going in detail. So the shortest integer solution, we're trying to solve a system of linear equations and find the certain vector S, the components of which are bounded, which means that smaller or less than certain number, and its matrix A is random. It's very solve this problem, just to put it simple. And it is not going to be our main problem of concern, just something we need to be aware of. This is more for one way for hashing and for digital signatures. So the problem that will be important for us is the learning with errors problem. And it's formulated in terms of matrices and components. Generally speaking, we have a certain matrix A with random components. We have a set of linear systems, linear equations. Actually, I'll show you an example to make it easier. Written down, and certain polynomials S and E with small coefficients are used to compute B. The idea is when you're given the values of A and B, it's very hard to the value of components of their S, and actually very hard to find the values of the error vector as well. So you have A and B, and you need to find the values S and E. That's a very hard problem. I'll explain it a little bit. Example.
So I know Chris Piker and Oded Regev had a lot of original work in LWE as applies to crypto systems. Chris has got a question in a second. I'll get to that in a second. And so I know that they had a very good paper that was, in fact, actually not too bad to read. Maybe that'll be one of the things we'll put on the docket also.
Yeah, and I'll show you some good example. Actually, after this, I have a slide with just explaining, how that would actually look, the problem itself.
And it's also had a question from San Diego. How is Q defined? I think.
That's a very good question.
Yeah.
I'm really wondering because typically Q is used, as a product of large pressure or something. So I'm wondering if there are other restrictions on Q.
So actually, that's a really good question because that matters quite a bit. What properties you want to have for the crypto system, and for a while, the early homomorphic encryption schemes used the Q, which was like some 500-bit integer. It was just, part of my language. It was a pain in the ass to use and everything else. And then more advances, like the double CRT representation, where Q is basically a product of like 30-bit primes, or 64 primes is the magic number. And so it matters quite a bit from crypto system to crypto system and functionality that you want to have. And so basically, I hate to say it, but it depends. And I think we're going to be looking at a couple of these different cases as we look at a couple of different crypto protocols over the purpose of this.
It's actually a very important question in parameter selection when we deal with parameter selection. It's a selection of the ciphertext module.
The depth of computation you want to support without bootstrapping and all these other kinds of things like that. Whether you want to deal with a 32-bit processor or a 64-bit processor, and all the good meaty stuff that actually matters when you start actually putting this stuff in practice.
Yeah, and it's a very important one.
Yeah.
So just another way to look at it. So generally, for any hard problems, we have the solution problem and we have the decision problem, and they often come together and they can be shown to be equivalent. And generally speaking, the hardness is that if you're given random matrix A and a random vector B, random meaning that the components are randomly uniformly distributed, it's extremely hard to answer the question whether A was produced using just a pure random generator, or whether it was produced by multiplying and adding by multiplying by the vector S, adding vector E. So those two, the input and output, look completely random. So and that randomness is what it makes the problem hard. And even answer the question, was this type of LWE formulation used, or it was just simply some random generator was used to produce those? The decision problem illustrates the complexity involved. So you have, in other words, input and output fully random, but the deterministic bracket is somewhat partial. It's actually, but still, there was given certain coefficients were used to certain vectors were used to compute this and how to find those vectors. And the most important is the vector F that translates to the private key usually. That's what is mathematically hard problem. And an example to illustrate this. So generally speaking, you see we have 4 components here. We have only 4. So in other words, the dimension of this vector F is 4, and we can round, let's say, 100 linear equations with a certain approximation sign, and the approximation means that we've used the noise. In this case, it could be just +1, -1 to each term. And the complexity of this problem is even if you're given 100 equations, and you understand that in the conventional sense, we would only need 4 equations to find a vector with components, will not be able to solve this problem in an efficient manner. That's because that error +1 or -1 makes the problem hard to solve, and normal Gaussian elimination that you would use in the traditional sense when you have a 4x4, I mean, in a sense, a linear system of equations with of order 4 can't be used because of that -1 error. So that's another illustration of the problem.
So one question that we're getting from Diego, one from San Diego, one from Henry. Would this, in a sense, be something like a least square solution over a finite field? And Henry says, I actually read some of that paper and was wondering if the example is correct, specifically 13S, 13S2, blah, 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 equals 16 mod 17.
So first of all, we have to keep in mind that everything we do here deals with integers. So all the operations are dealing with modular arithmetic, not the real number case, which, I mean, in this case, certain things are much easier to solve. So so I guess the maximum likelihood and et cetera scenarios that were discussed, when you are solving this problem, it actually it basically diverges at a certain point because of the new terms that are introduced, and that results in exponential complexity. That's what happens. So one of the corners of this is because we're dealing with integer numbers, discrete space. So the operations are very different. In this case of mod 17, so that, and the second is of course the underlying problem. So if we formulated this without mod 17, then that would be a different case. So without modular arithmetic. So it's a combination of those two factors that contribute in this case. And there's one paper that I'm referencing that discusses in detail what approaches you can use to solve this system of equations. So it's actually, I think it was by record. I think it was by Chris Parker. In reg, I think it's in the reg of problem, but I have it listed in the references. So, sure. So it's rather conceptual. So that's why I actually took that system of equations from there. So it goes step by step. Well, let's try this idea. Let's try that idea. And just we're going to discuss this next time. But generally speaking, if regular with errors, we have to deal with matrices and deal with matrices. I mean, with lattices, the full-dimensional lattices, to generate one. We can say B, so one number in that vector B. We really need to sample the full vector, and which makes it very inefficient to generate. For example, one vector with numbers, uniformly distributed numbers, you would have to generate basically, let's say it's n space. You would have to generate n vectors. You would have to generate the full matrix to solve this problem, and that's what made LWE itself very inefficient. So until recently, this was more of an interesting from the mathematical hardness perspective problem, but it was not practical. And ring LWE, which we're going to discuss, I mean in the next lecture, actually the fact that we can use a special structure that lattices, ideal lattices, to use one vector to generate all numbers in that B in one shot. That was the idea.
So it feels funny to say this now that I'm on the other side of the table, but until recently it was considered an academic exercise, and now it's maybe for me it's an academic exercise, but it's some use, right? So yeah.
We'll discuss how this is possible next time, but
yeah.
So the other slides are we can go.
Yeah, let's put this off for next time. I think we're running a little bit over.
Yeah, because they're very conceptual. So generally speaking, so I don't know if it's okay.
Maybe we should just this time in case there's any discussion you want to have here, or if there's any questions or anything else that someone might want to make on from the online side also. Questions? That's a gold star for today. Well, we'll get some more email later. Sorry, go. Okay, something. So, thank you very much. This is going to be big all you good people in San Diego and other places. Thank you. I'm sorry, Megan, were you trying to say something?
But we really appreciate this. I think this has been really helpful, and I look forward to the rest of the lecture series.
Yes, thank you.
Great.
And it'll be more fun next time, I promise. I mean, we had to go through, this somewhat abstract, slides today, but the next one is going to be more practical. We'll actually get to see some ideal editors. And,
Okay. Well, I mean, who remembers their abstract algebra after abstract algebra?
Hopefully we'll make it memorable for you guys.
This is actually the part that I really love, and I really appreciate, being able to stop you guys and have conversation, so I don't mind it going long. So that's my input.
Yeah, we're gonna. Like I said, coming from ministry, I know time is money and everything else like that. So we're gonna try to keep it about an hour, give or take. But if it does run over, if there's good conversation going, that's perfectly fine. I'm perfectly. This is about building and group understanding.
Absolutely.
Yes. Okay. So thank you, and we'll see you next week, same bat time, same bat channel.
That sounds great.
Thank you. Bye.
Take care.
Thank you. Bye. Bye.